Hi everyone and welcome to this lecture. Today we want to talk about the SIR model. That is a model used by epidemiologists to model different kind of pandemics and epidemics. So since we are currently passing through a hard time with COVID-19, um, it would be good that if we can get some insight that how these epidemics are modeled using mathematical equations. So this S means the susceptible, I means infected, R means recovered, and I'll explain these terms as I go on. So before we want to use the equations, that is, this SIR model is just a system of coupled first order differential equations. We have to declare some parameter, and one of them is pre-infect, and this pre-infect means the pre-infection period, that is the amount of time the virus spends in a incubation period. So for COVID-19, if you are talking about COVID-19, that's roughly 7 to 10 days, right? So let's call it 7 days because we will consider the worst case scenario for our demonstration. And F is a quantity that will appear as 1 upon the pre-infection in our equation, so it's helpful to introduce that as well. So just a pre-infect, all right. And after that, what we want to do is we want to declare the contact rate, that is R0, and this R0 means that how many persons a single person would infect, that is, if someone is affected with the disease, how many persons that person can reach and put them into the susceptible population. So for us, let's say 25, R0 is 25, R0 that is. And after that we are going to use something called a duration. So this is from where we will begin the simulation, and this duration is, let's say, 21, and there is something called R, which is 1 upon the duration, which is more like a recovery rate, which can be thought of as a recovery rate, to be frank. So and these things will be constants. And note that this is a hypothetical model. It doesn't bear any resemblance to reality, because in reality you have to get a huge chunks of data first to apply the SIR model. But in our goal for this class is that to see how we can learn about some properties of this SIR model and how we can see different kind of stuffs that are floating around. So after that we want to declare something called beta, and this beta will be our a parameter, and this parameter will give us the contact rate, that is, it will involve this R0 as well. So just type R0, and in the downside over here, oops, that is on the denominator, it will be the total population times the, let's call our total population as, okay, let me just declare total population first. It hasn't been declared yet, so we want to type total population equals to, let's say, 200 million people. We want to see this thing in a very large scale, so that's why I'm choosing 200 million, and it will be just the total population times the duration. So we are almost done setting our parameters, and next thing we want to do is that we want to declare something called a time span, and this will be 365. This means that we are running the simulation from t equals to 0, and after that that is small t equals to 0, and we want to see the scenario after a year. So let me just see if this is working. Yeah, so for our differential equation we will have like 5 initial conditions, and let me just put them inside a list so that I don't have to go through the hassle of writing. So let's call it init, that is the initial conditions, and that will be our susceptible cases at the beginning of our simulation will be the total population. because we are assuming that all the population will get infected or they might get infected. The exposed people are just 0, no one got exposed. Then we want to have the infectious people. We also say no one got infected. So you can see that this model is not true, because without these data there is no way to tell that whether this germ or virus is actually in the region or province that we're trying to simulate. But this is a toy model, so let me just write a toy model over here. Yeah, now it looks good. So we can do whatever we want with the initial conditions and see how things changes. Okay, so 0 infections is a bit suspicious. So let's have 3 people or 4 people got, let's take, not 7 people got infected. All right, and after that we want to set some conditions for our recovering people, and this recovering people will be denoted by capital R. Don't confuse with this with R0, which is just the contact rate. So this will be our recovered people. The R is a function that will give us the recovered people, and initially there is no recovery. And finally we want to have the number of deaths. So at the initial time there will be no deaths at all. So this is set. Then we want to have our equation, right? And since this is a coupled differential equation, we're going to use ND-solve. So first you type solve, then you use ND-solve, and then you just do the long work of writing all the equations there. So this will take a bit of a time, but let's just try to write them down, and I'll try to explain every term while I do so. So the first thing is the how things are susceptible. That is, we want to have the equation for susceptibility, and this will be minus beta times I, that is infection, times the susceptible itself. This is one equation. Then we want to have the exposed population. This will be given by plus beta times I times S of t. Oops, this became an H instead of a star. Okay, then minus F times E of t. Okay, 2 equations are done, 3 left. So after this we want to write an equation for the infection. So the rate of change of infection with time will be just equals to F times E, that is exposed, T, minus R I of T. You can give a multiplication sign, or you can just leave it empty like this. Just try to remember that you have to give a space. As long as you give a space, everything is fine. So after this we want to have the recovery function, that is the rate of recovery. This will be smaller I t, and after this, so this is a recovery equation, and after that we have only one equation left, and that is the death rate. So we just have to have this death rate over here. D prime of t is equals to dr, that is our death rate, which we haven't specified. So let's try to specify the death rate as well, because we need a death rate. So let's say the country we are dealing with, or the imaginary place we are dealing with, we are calling a death rate something as 2.1%. That means, or let's try to reduce our death rate. 2.1 is way too much. So instead of 2.1, let's take death rate to be 1.5. So it will be 0.015. So 1.5 divided by 100, that's what it is. So yeah, so after this is done, just type tr, and it will be proportional to the infection itself, because only the infected people die, right? The rest of them are just healthy. And after that we have to specify our initial condition. So let's first try to use this init, and we are technically done. After that you just have to specify the variable, that is s e I r and d. So you have to declare them inside a list, that s. Second we call d, so we have to type e, then we have I, then we have capital R, finally we have d, and our t is independent variable. So let's try to suppress the output. Let's see. Okay, so this is saying that function I appears with no argument. So maybe we have done a mistake somewhere. So yeah, this is the place that we didn't type I as a function of t. So let's try to do it. And yes, we didn't specify the range as well. So t will start from day 0, and let's call it to 365. Let's see what happens. It's taking a bit of time. So I think Mathematica already generated the output, so let me just see it again. Yes, Mathematica successfully generated all the outputs, and as you can see there is a s interpolating function, e interpolating function, I, d, r, and you can already see that how they look from here. So after this we'll try to plot it. So let me just try something, that I want to plot sol, which is a function of time, or let's just call it sol, because it's coming as a list and it's also a function of time, all of them. So from 0 to 10, let's just see if we can get something. See, we are not getting anything. So let's try sol t. Yet we are getting nothing because it contains a list. So what if I do list plot? Will I get something? No. So what do we do over here? We have to do a bit of hard work right now. That is, we have to declare functions for the susceptible, the recovered, the dead, and all that. So let me just suppress this output. And now comes the most painful part. That is, we have to declare some functions. That is, let's call susceptible. I hope this spelling is correct. Susceptible. It's a function of time. It will take something from our solution, that is s of t, and it's getting replaced by this way. Similarly, you will have to assign all this. So let me just do that. Here comes exposed. After exposed, you have to get the infected population. It's also a function of time, and this will come from I of t, sol 1, and after infection comes the recovered. So recovered population. You will have R of t, and finally we have to type the dead. and this will come from the solution as well. So just a solve, and let's try to run all of this together, and yeah, everything is fine because there is no error output. Now you can plot them together. So let me just type plot, and you want to take all of these functions that is inside a list. So susceptible of T, infected of T, then we want to have exposed of T, then sorry, okay, it doesn't matter because all of them are getting plotted in within a same frame. So we got susceptible, infected, exposed, then we have the recovered patients, and finally the dead. And for how many days we want to see it? We want to see it for initially from 0 to, let's say, 100. We want to see what happens in the first 100 days, and I want to take care of all my labeling with plot theme details so that I don't have to specify anything else. And then I want to label the plot. So plot label, this will be SIR toy model for COVID-19. Let's run this plot. There you go, for the first 100 days. So this is a good plot. You can see all of the things, and if you want to see what happens throughout the year, so you have to go for 0 to 365, and this is your plot again. And as you can see that the curve, if I can make the image a bit large, you can obviously make this image large from here as well. So let me just try to get these coordinates, and you can see that this infection line, that is this one, it's going up and up and up and up and up, and suddenly this is going down. And the death curve also flats at some point as well, and this is around 100 to 130 days, I guess. So this is the kind of thing that you would expect from a pandemic situation. Obviously we need more data and more stuffs, and these initial conditions and these rates have to be really accurate for this to work in a very large scale. So let me just drag down the image a bit, and you can see that the recovered part, okay, so the recovered part didn't got plotted, is it? Did we miss the recovered? So yeah, we missed the recovered here, because even though this is showing that recovered of T, but we cannot see this graph, right? That's because instead of using capital R over here, I use the small r. So let me just plot it again, and now you can see that this is our recovered patients or recovered people. And instead of 365, if you just go for 400, obviously that won't work. Why? Because the interpolation functions were only valid for 300, and you can see that this is just nothing interesting over here. So it's a good idea to first see that the range that you are using the ND solve thing. And let's try to make our image size medium. Okay, it was medium, so I don't want a medium, I want a large. Yeah, this is good, this is pretty visible. And you can also change the background if you want, you can take off these grids if you want, but it's a good idea to have them. And you can see that almost within 130 days the curves start to get flat. So let's try to see the interval, let's say 140, 0 to 140. So yeah, the curve starts to flat around the 100 day that the virus is introduced to the region, and around 140 it starts to get flattened. So let's take 155. It's almost there, so let's take 170 again. 170, and this is almost flat. So this is our plot, right? But what if I want the exact data for day by day? That is, I want you to make a table and I want you to make a data out of it. You can also do it in Mathematica. This is pretty easy. So let me again just keep it 365 so that you can view the full information for our modeling over here. And now to make a table, so let me just give a small heading called table making. And in this table making, what we are going to do is that we are going to call a table. So let's call it data table. And here what we want to do, what you want to use that command table, and inside this table you have to first give something t, that is will be our day, and after that you have to run this function that is susceptible. Then we want to have exposed, then we want to have people who got infected, then we want to have people who got recovered, so this is recovered, and finally the death. And now I want to iterate over t and extract this data that you see in this plot in a table. So this is pretty easy. Again, I want to iterate from t0 to 365, and obviously I'm going to suppress the output so that it doesn't become a mess. If you do it, you can already see that it's done. It's showing the suggestion bar. So I don't want to see the suggestion bar, rather I want to have my whole thing as a grid, that is as a table. So let me just type grid, and inside this grid you can put this table, that is you want to put some expressions that comes over as a list, and since this will come as a multi-dimensional list, so sorry, a single dimensional list with multiple entries, you can use that inside it. So if you just use grid data table, yeah, this is a good thing but still not quite complete. And you can see that t means our days, that is day 0, day 1, day 2, day 3, and blah blah blah. So before you go for the grid command, there is something you want to do, that is you want to name these things, and you want to have these names appear on the top of this table. So for that you need to use something called a prepend. So append are kind of commands that add things later, and prepend is something that will give you the headings that you want at the top. So what we're going to do now is that we are going to use prepend. So let me declare another variable, that is, or you can just even use this thing over here. So let me just use prepend over here, and the first argument will be the table itself, and the second thing will be all these things, that is susceptible, exposed, and instead of t we'll type day. So how do we do that? We declare them as a list, and one thing you have to keep in mind, they will come as string, so day, and after that I'm going to type susceptible, then I want to have exposed because I wrote exposed there. So let me just write all of these things down. You get it. This is pretty easy. And the last thing is the dead people, right? Okay, run it. It's done. As you can see that this is saying that show suggestion bar. Obviously use grid again to see whether you are getting the thing that you want. Yeah, now we are getting what we want, and this looks pretty neat, but still the bars are missing, right? It doesn't look that good, because if you want to make a report, then a table should appear as a table. So to make these grids, we are going to use the grids. By grids I mean the bars. We are going to use another attribute, and that attribute is called, okay, let me just write it down for you. It's called a divider, and using the divider we will make lines along this, and that is on the horizontal and on the vertical axis. So to put these lines, we are going to use the divider thing, as I already mentioned, and you can do that by just using this grid. Inside this grid you can have our table first, that is this table, right? And after that you are going to call this attribute called divider. If you just type di, you can see a suggestion called divider, and you can go for all and false. So all, let's see what does this give. Since this all and false will give you a divider on the rows but not on the columns itself. So to do that, all, let's see, and there you go, a very nice table of the data we just generated from our model. And from here you can actually guess the things that we guessed from the graph. Is that around day 120 or 119 the curve will start to get flattened. Obviously these numbers are quite arbitrary, quite large, because our population sample is very large, is 200 million, and obviously we assume the worst case scenario. So this is how you can generate data, feed them into tables, and you can even export this table as a CSV file just by using a simple command called export. Just like we used import, you can use export. So this very small piece of code can actually generate a huge chunk of data, and within seconds. So this will be it for today, and I hope you liked it, and that will be all for today. Thank you.